to be a bit more technical. So I'm going to first be moving the speaker view away from my screen. Good. All right. So for those of you that were not here in the morning for Peter's talk, I would like to sort of start by saying that, so I believe, and many of us believe by now, that there's typically at least 3 classes of aims when we're trying to use data to answer a scientific question. And let's say the Harvard School of Thought would say that these goals are roughly divided between description, prediction, and counterfactual reasoning. And I would say these approximately align with Pearl's ladder of causality and also sort of operations that one can do formally on a causal graph of Spitzer and Chetkin. And these are association between the variables. Then we can think of an intervention we can do to try to maybe see whether we can change the future. And finally, the counterfactual, which is possibly contrary to fact. What would have happened, for example, would I be a professor now? Have I been born a man? To take a random example. But for example, I'm going to say that those questions are difficult, as we were seeing in the morning through the discussion with Romin and Peter, and even the discussions with Niels. And I'm going to be thinking that you are the scientist, and I'm going to be able to trust you that you're gonna think really deeply what question I'm trying to answer, and what is the corresponding estimand that I want. Am I thinking simply about prediction, or am I really thinking about something more explanatory, or something a bit about intervening in the world as is, so that I can take a course of action and change it? And hopefully by now we're convinced that many of these decision-making tools that we're trying to do by using predictive algorithms or predictive models are really better aligned to counterfactual thinking. So let's see. Oh, no, this doesn't work. Okay, so I have a quick exercise to sort of set the scene again. So imagine we have a heart consultant, and he or she has 108 patients, and here they are. And we have the measurements of these patients, you know, their age, weight, exercise habits, smoking, blood pressure, lots of things, genetic conditions, comorbidities. And so we have 3 questions of interest. So first is, what is the risk of heart failure, let's say in the next year? This is a bit like Niels' question. But also we want to know, what is the risk if they were to stop smoking, they took more exercise, and they started eating healthily from today? What would be the risk in a year from now? And final question is, who should I get to recommend a heart transplant from amongst these 108 patients that I have here? And so these questions are all a bit different. So the task for you, so I would like to ask Jessie if she could bring up my poll, is can you, for each of these questions, decide whether they're pure prediction or whether they require some sort of counterfactual, sort of hypothetical thinking? And so, you know, you don't need to overthink it a lot. I think by now, maybe we've seen that it's not as clear cut, but so how are we doing for our participation, Jessie?
37. Oh, we're going up. We're almost on 50%.
Good, excellent. Because my talk is a bit long, so I wouldn't want to wait too much. But I am curious to see whether my colleagues convince you already. So can we see the results, maybe? Right. Okay. So I'm sort of liking what I see. I think, yeah, I agree that sort of the first one is pure prediction, and the second one requires some sort of counterfactual thinking, and it's because I'm trying to modify the world as is and intervene. So if we were a bit more formal, I would be saying this is in the middle, in the intervening. And then the last one about who should I recommend a heart transplant, that does take counterfactual thinking, because I'm going to have to try to contrast what would be the future of this person, how they get the transplant, versus what would be their future had they not get the transplant today. And then if the contrast is sufficiently beneficial, taking into account all the possible downsides, I would then recommend treatment. All right, so we can close this poll. So I'm going to say that maybe we've convinced ourselves that predictive algorithms are not in themselves adequate decision-making tools. So if I need to take a decision, if I need to take an action, it's almost by definition, I am questioning whether I should intervene in the world as is. And therefore, it is a combination of these two things. I need to take a causal framework, and I also will need to predict outcomes with and without this action that I'm trying to make a decision about. And so, as we said, comparing the risk benefit of heart transplant versus medical treatment is, for example, a little bit of a combination of both things. If I'm only interested in what would be the risk of death, then that's just a predictive model. But if I'm looking to intervene, then I will have to do something a bit more causal. So why is counterfactual prediction different from usual prediction task? So it aims to predict the potential outcome. So I'm going to be using this notation where the superscript is going to be the outcome that would have been if the person is treated, and Y0, the outcome that would have been if they were not treated. So imagine I have here now a patient with 64 male, and I have a bunch of their characteristics. And so now I want to ask myself, what would be the outcome had this person received, for example, the treatment heart transplant? And what would be the, and so this person is healthy at 12 months, as opposed to what would be their outcome if they don't get the heart transplant. So they go down this other path where they're not treated. And maybe in this example, this person is hospitalized at 12 months. But what is crucial about this counterfactual prediction is that I only get to observe one of these outcomes in real life. The choice is not random, because obviously the clinician that is taking this decision at the time the decision is taken is going to take into consideration what they already acquired in terms of knowledge and in terms of what is known to the whole of society about what are the chances of this patient benefiting from treatment. So when we're trying to do counterfactual predictions, we're going to have to try to disentangle this kind of confounding by indication, as is known in the trade, let's say. So the aim is to predict the potential outcomes. The ground truth will remain unknown because it's counterfactual for one of the treatments at least. And I only have the data that has actually happened in the real world, right? So I'm going to have to use causal assumptions in order to be able to assume that if I condition on enough things, if I find enough people that on average are like my patient that is here right now, I can then assume that the outcomes of these patients, like my patient, are similar in terms of they are exchangeable, right? And I also have to assume that for all the patient characteristics that I'm considering, which I'm going to summarize by L to simplify things. So at every sort of combination of the characteristics that I have for my patients, the probability of getting treated or not treated is, is not a certain treatment. The treatment course of action is not certain for any combination. So there is no complete counterindications, and there is, the decision, there is a true decision to be taken. And then also the technical assumption that that there is consistency, by which I mean that if a course of action is taken, then the observed outcome is actually coinciding with the potential outcome for that level of treatment. So if these causal assumptions are met, then we're in luck. And then I can use actual observed data to try to build a predictive model to predict counterfactual mean outcomes, right? And so let's, for example, here I'm concentrating on what would be the expected outcome under treatment. And then I'm going to try to then estimate this counterfactual quantity by estimating the mean of the outcomes on those patients that were treated and conditional on all these confounders, because I know that the choice is usually not random. So my remit within this workshop was to think about the challenges. So Niels has done already a great job to convince us we need counterfactual thinking, but it's not as easy as knowing that we need it. So, so we still need to overcome the challenges of getting there. So one of these challenges is about this positivity, this condition that looks kind of quite technical, is actually quite deeply related to the decision that needs to be taken. So this doctor here, she needs to be in equipoise as to whether to treat the patient or not treat the patient. If there is no doubt about the course of action, then there is lack of positivity, right? If she already knows that for your characteristics, she will always treat you, then there is no decision to be taken, right? So for example, maybe no patient over 85 will be given a heart transplant. So what I do in this case is I will have to carefully rephrase my question so that everybody's clear that the predictions I'm about to make don't apply to that part of the population, right? So there is other type of lack of positivity, and this is called random positivity violations. So there is no strict contraindication, but perhaps in a given sample, there happens to be no patient with those factor characteristics who gets given the prescription. So for example, in this statin versus no statin example, we see that there is very different distribution of probability of being treated with statin between the not treated and the treated, right? And so this kind of is one of those challenging situations where, although we do have people more or less treated and not treated, probability of being treated and not treated in both camps, we see that there is regions where we say little overlap, right? And some people will say no overlap means there is no ambivalence between recommendation. So we wouldn't build a recommender system or a counterfactual prediction system to support decision making. So this assumption of overlap is actually very important for building counterfactual predictions. And more importantly, these counterfactual predictions are going to be based very heavily on careful extrapolation. All right. So so this is what we want. We want counterfactual prediction for a particular level of the treatment. We said we're going to be assuming that given the confounders L, so given all the things I put in the model, I have roughly, approximately the same distribution in the observed group, so the actual treated people, from the ones that would have been treated in the counterfactual world. But importantly, this is another difference between counterfactual prediction and the regular kind of prediction, that the predictions will always be out of sample, right? Because this didn't happen for half of the people. So we're going to have to be extra careful with extrapolation. Aside from extrapolation, we also need, once we start estimating these conditional expectations, I'm going to need to put a model on these things. And so I'm going to need to assume that this model is correctly specified. This is not different from regular prediction. Whenever we model something, we always have to assume that the model we chose was correctly specified. How do we do this? Normally, we would check it from the model. We would then adapt, add more terms, tune hyperparameters if we use in machine learning. But this would bring the concern of overfitting. And while in the world of pure prediction, I have my training data and I can carefully see that I have not overshooted and really overfitted like some of these cartoons here. In this setting, remember that by definition, I don't have the whole of the sample I want to make predictions for. So overfitting is more of a concern. So the problem of poor overlap is not just a theoretical concern. I wanted to bring, for example, a real example of an economics application. So for policy decision, for example, governments often use cash transfers for those in conditions of poverty to incentivize them to, for example, come to the health clinic. And obviously, for obvious reasons, because of resource constraints, you don't give the cash transfer to people that don't qualify. So for example, nobody that earns over $100 would get a cash transfer. So this creates a lot of poor overlap. And so if we're going to build counterfactual predictive models for this, we're gonna have to do something to sort of deal with this. So lack of overlap is related to something that is known in the machine learning community as, oh, I forgot the word. So what is it? Covariate shift. And we'll see it in a second. So the treated here are sort of with the little crosses on the right-hand side, and the untreated are these little diamonds or little dots. And we can see that there is little overlap in their L values. So I'm obviously exaggerated this, and I have the treated on the high values of the L. And now I'm going to try to fit a model for predicting their Ys. So I fitted a linear model with interaction, and I get these two lines. But maybe instead of doing that, I could have also fitted a model with a quadratic term. And in terms of the actual observed data, there is very little to decide between these two models. And so now we can see that when I'm using these models to predict for these people that were untreated, the predictions are going to be very different whether I use this model or this model. Right? So extrapolation is not just it's not just a little concern, it's a huge concern, especially in regions of poor overlap, which is especially a challenging situation in sort of confounding by indication. Right? So when we're building these counterfactual predictions, we have to be careful about this. And we can think about it this way. So I'm trying to build a predictive model for the treated. And all I have is the ones that were treated in reality. So after I have adjusted for the L's to try to deconfound and then marginalize over the L's, because I only want the probability of Y1, not a conditional probability. This step here kind of basically relies on the distribution of the L being the same in the untreated and in the treated. So is this crucial step why it matters that the characteristics of the ones that are treated in real life and the ones that were not treated need to be the same. So poor overlap is related to covariate shift. So if I'm training my predictive model only of those that in real life got the treatment, then I have to be careful that perhaps my training set doesn't have the same covariate distribution as my testing set. So the set for which I want to make the predictions. This gives us the idea that, oh, so maybe on top of, well, not maybe, but for certain, on top of dealing with confounding, when I'm building these counterfactual prediction models, I also have to do something extra to try to deal with the fact that in all likelihood, the distribution of the confounders are going to be very different in the ones that are treated and the ones that are untreated. So when I'm trying to construct a predictive model that I'm trying to, for example, minimize the loss function, the mean square error, I'm going to have to think of a way of modifying this loss function so that I deal with the covariate shift, right? So in practice, I can't really deal with this loss function because this quantity here is counterfactual, so I'm going to have to deal with an empirical analog. So this gives us a chance to then do something to sort of have a good math guess as to what do I substitute this with in the loss function. And so some proposals from the covariate shift literature are to reweight the loss function in one way. So Shimodaira here suggests reweighting it by a density. And I have current work with Stijn van Steeland and a colleague, Jamie Burns at the London School, where we're trying different proposals and they seem to be working fine, but that's like a talk for another day. So another challenge that, I don't know, now I have an example that I think we've touched on this before. So this is this famous Caruana example that Matt was discussing during his introduction. So they train a model to decide whether patients that were presenting with pneumonia to the hospital should be admitted to the ICU. And the training data happened to come from a hospital where asthmatic patients that presented to the hospital were almost surely transferred to the ICU. But this was ignored in the training model. So they completely ignored these sort of characteristics, which ended up with a model that predicted that asthma patients with pneumonia were less likely to die, which was, as Matt said, kind of like counterintuitive. So I claim this would not have been solved only by setting it as a counterfactual problem, but they need to go a bit further in recognizing that the training and the deployment settings had different policies, and they need to use this sort of covariate shift methodology to kind of correct for those biases that creep in that way. Not moving anymore. Okay, moving too much. Okay, there we go. So I've said all right, like that. Right, so two more challenges that we still encounter when we're trying to do counterfactual prediction. So often it's not enough to just give me a mean prediction, and I want to know what's the quality of my predictions. But now remember that I don't have the ground truth, right? So I can still try and construct prediction intervals that would tell me with a certain probability I will cover a new observation, right? So if my models happen to be parametric models, I can still use sort of regular prediction intervals. But the problem is, how do I construct now valid prediction intervals for machine learning prediction models? And the second question is, given that when we're talking about counterfactual prediction, we have to be a bit more careful about covariate shift. How do we incorporate covariate shift into the construction of our prediction intervals? So there is some novel proposals from Ryan Trisciani and his group. And yeah, so I think this is quite promising new literature. And the final point is, in which these counterfactual prediction models are different from the traditional ones, is the whole step of validation, which is very important in clinical prediction models. How do we validate the model in the absence of ground truth? So there's some novel work from Michaela van der Schaar, also of the Turing Institute, which uses influence functions, but perhaps we could even do something a bit more, more modest. And I wonder whether a simple idea as is to use trial data for similar clinical question, perhaps reweighted so that the trial population represents the target population. Can we use trial data to sort of try to validate our counterfactual predictions? And so this is another idea that we would like to explore as part of the outcomes of our theory and challenge fortnight. All right, so I think with that, so we by now probably know that we do need to go further from pure prediction, and we recognize that there's questions where we need to bring counterfactual prediction modeling. But the problems don't stop there. So if overlap is poor because the treatment that we're trying, or the exposure that we're trying to study is so that the characteristics of the individuals that get or not get the exposure are very different, then we need to be very careful about making dangerous extrapolations. To avoid most of these extrapolations, we could try to adapt techniques from covariate shift, but this needs more study. We are also more concerned about model specification because of these inherent extrapolations, and then the challenges of validation and constructing valid prediction intervals. And so a little bit of references. Thank you.